Okay, this lecture is called Light Me Up. It's an introduction to circuits. In the immortal words of Hunter Hayes, you light me up like fireworks flying on the 4th of July. Yeah, you light me up like sunshine blazing in the summertime sky. So, we are going to introduce the idea of circuits. And the purpose of this first lecture is that you be able to convert between a circuit schematic and a physical circuit board, and that you be able to distinguish between a series and parallel connection, because they're both good for very separate things. And then that you understand the role of a circuit breaker and fuses and how they operate and why we have them um, for what we use them for. Okay, the first thing is what we already know. What we already know is that we have this idea of electric charge, that positively charged plates or positively charged particles will be attracted to a negatively charged plate because opposites attract, in other words, Coulomb's law. And that negatively charged particles will be attracted to a positively charged plate for the same reason for Coulomb's law. So this is something we already learned in the previous unit. So now let's take a look at what we know now. Based on the lab, we learned what the function of each one of these particular devices was. And in this particular case, you can say that the function of the first device was it was a fuse. And what a fuse is it's something that allows you to cut off the circuit depending on what it was. We learned that this is an ammeter. Ammeter. We learned that this V was a voltmeter. We learned that this was a closed switch. We learned that this is an open switch. We learned that this is a battery or a voltage source. You may or may not have explored the idea of this as a capacitor. This right here is a resistor, which is a lot of times we use light bulbs for resistors. And then this right here is once again a fuse, but another word for a fuse would be a circuit breaker. Circuit breaker. Okay, my handwriting is a little messed up today. So, once you do this, we learn that there are different functions for all of these particular activities. So the first one is you have a voltage source. A circuit begins with the positive end of a voltage source. This is the start of a circuit. Okay, or if you were using one of these, this is the start of a circuit. Okay, you can have lots of different voltage sources. One potential voltage source is a battery, another is plugging something into a wall, another is this variable voltage supply. You can even rub your balloon on your head and then you create a voltage source that way. So there's lots of potential things that you have as far as voltage sources. But the voltage source provides the push that moves the charge through the circuit. So you're moving some sort of energy, some sort of charge through the circuit. And that the voltage provides that push. The next thing you have is you have a connection, and specifically we call it a wire. And a wire is just a straight line symbol. Okay, so it's really nothing, but it's what allows the charge to flow through the circuit. In order for you to have a functioning circuit, you can't have any breaks in the circuit. So you have to have a connection, or you have to have a wire that's connecting whatever electrical devices you're taking a look at. So we have that, and then the next one, oh, anytime that you want to make a connection, you want it to be a conductor. Okay, if you have to have it be a conductor, otherwise charge won't be able to move through it. And a lot of times we look at a water analogy. We say a wire is like a pipe that allows water to flow through it, but instead of water, we're talking about charge that flows through it. The next thing we want to look at is a device called a resistor. And a resistor is anything that uses the energy of the circuit. The electrical energy is turned into something else. And usually what it does is it impedes the flow of charge. So there's something to kind of back it up. So you've got this idea of this resistor, and what it's doing is it's stopping the charge from moving through and using that energy to usually generate heat. And whenever you have heat, something gets really, really hot, sometimes it glows. And so that's how you get a light bulb. At least that's how a traditional incandescent light bulb works. Now, the water analogy for a device would be an example of a turbine. And what you're doing is you're using, with a turbine, you have water that flows this way. So the water is going this way, and you stick a wheel that's kind of like a windmill, but for the water, attached to it. And the water will actually push the wheel, causing the wheel to move. So I'm using the energy of the water to make the wheel move. Well, I'm doing the same thing with electricity in kind of a roundabout way. You're using the energy of the electricity in order to accomplish another task. Next, we have a switch. We have a switch that is an on-off switch, is generally the most common term for it. I will tell you that the on-off switch is not really on-off. It's really more open-closed, and we'll explore that idea a little bit more as we move along. But a switch is an insulator. A switch is an insulator whenever it's off, and it is a conductor whenever it's closed. So because of that, you have this idea that a switch controls the flow of charge, and so because of that, you can think of it as a faucet. Next, you have an ammeter, and an ammeter is what measures the amount of electrical current that's moving through. So an ammeter is really important that it must be wired in series, and you're saying, well, what does that mean? We're going to talk about that in a little bit, but for now, an ammeter has to be wired in series. And what the ammeter does is it actually measures the amount of charge flowing through the wire. An ammeter has very, very, very low resistance. Because of that, it's a good way to measure the amount of charge moving through the wire. This is what an ammeter looks in real life, and you have to be very careful when operating an ammeter. You have to make sure the black cord is always going to be attached to this. This is the negative terminal. But the positive terminal is going to depend on how much charge you're trying to measure. This 50 is a very, very, very small value. It's actually 50, in our case, milliamps. Okay. The next setting is 500 milliamps. And the next setting is 5 amps. 5 amps is a lot of current. But you always want to start off with a 5 amp, and the reason why is if you have a really large current and you use a really small value, what you're going to do is you're going to blow a fuse in the ammeter and it's not going to work. Next, you have a voltmeter. A voltmeter measures the potential difference or the amount of voltage that a circuit has. It's wired in parallel with whatever you're trying to measure, and generally speaking, it has a very high resistance. It does measure the push of the charge, or the push that pushes the charge through the circuit. This right here is a voltmeter. If you notice, there's not extra devices here. You just connect the black end and the red end to the sides of the devices that you're trying to measure. Next, you have a fuse or a circuit breaker. This is an example of a burned out fuse. But what it does is the fuse of the circuit breaker is a safety device. And what it does is if there's too much current moving through it, it gets really, really hot and it melts. If it's not melted, it is considered to have a resistance of 0. But if it's melted, it's considered to have an infinite resistance, okay, because the resistance value, there is no current moving through it at that point. This symbol is what we're going to use for both a circuit breaker and a fuse. So if you look at this example, it says draw a circuit schematic and describe the circuit in words. The first thing we need to do is we need to start at the source. We start with this idea of this circuit right here. You have that right there, and that is the positive end of the battery. So what I'm going to do is I'm going to draw the symbol for a positive end of the battery. And the positive end of the battery is the longer one. And then what I have is I've got a wire that comes right here, and sometimes it's kind of tough to tell what the wires are doing. You've got to be really careful as far as what you're doing. But you can see that this wire right here comes around here, and it connects to this point right here. Okay, so I draw a connecting wire, and I get to the point where it splits. I've got one wire going this way, and I've got another wire going this way. So I'm going to draw that on my diagram. Okay, I'm going to draw where it goes down, and I've got that connection point. Okay, that's where it splits over. Once you have where it splits over, okay, now you draw what's next. And on this one, I have a light bulb. Remember, a light bulb is another symbol for a resistor. And you have one on the other side as well. And then you draw them. If you follow them, they connect back together. If they connect back together, you draw them in their connection. The next thing that you do is they proceed via another wire to a switch. Okay, so you draw the symbol for a switch, and I'm going to erase what I had previously done so we don't get confused. You have a switch right there. Now the switch is open. Okay, excuse me, the switch is closed when you look at it. So when you have that, you have to draw it as a closed switch. And now that you have the closed switch, you follow this back around, and we go into an ammeter. Once I go into the ammeter, that's the next symbol that we do. You have this ammeter as a symbol of a circle with an A. And then next you follow the ammeter, and it goes all the way back to the other end of the battery. This right here is a circuit schematic for what you see there. Now this circuit schematic may look very different from yours based on where you decided to turn it. As long as you have the correct elements in the correct order, then it's going to be considered correct. This one says a circuit consists of a 120-volt source connected to two resistors followed by an ammeter and an open switch. Draw a schematic for the circuit. So we have a 120 voltage source. That's our battery. We leave the positive end and we come into two resistors. Here's the first resistor. Here's the second resistor. Next we come to an ammeter, which is this. And then next we come to an open switch. And then follow, since that's the end of it, we connect the other side all the way to the other end of the battery. Next we need to talk about the requirements for a fully functioning circuit. The first is that you have a voltage source. You have to have some sort of voltage. Plug it in a wall, battery, something. The second one is that you actually have to have a closed circular path. Okay, it doesn't have to be circular. You have to have a closed path. In other words, you can't have any place that the electrical charge can leak out of. And finally, you have to have a device that uses the energy. The energy has to go somewhere. And the device can be the actual wire itself. Wires do have an inherent resistance, and so because of that, you can have a circuit where the wire is the resistance. Generally, we call that short-circuiting something, so we try not to do that, but at the same time, it does work. So, if we look, drawing circuits, we always start from the positive terminal of the battery, and we draw through to the negative end of the battery. And if you look, it requires a closed path, a voltage source, and it requires something to use the energy. So the idea of drawing circuits is based on conventional current, which is the idea that you have a positive charge that leaves the battery and moves through the wire. We know that's really not the case anymore, but we still use that convention when we're drawing circuits. So in this one it says which light bulbs will be illuminated when the circuit is closed and connected to a voltage source. Okay, if you were to look at this particular case, you're looking for you got to have a complete path. If you look, this light bulb is missing its light bulb. So because of that, you have a break in the circuit. In other words, there's something that the charge can't get through. So because of that, no matter what you have, these light bulbs will never receive any electricity, no current. So because of that, none of these will light up. If you look at this one, it says if bulb A were to go out, so bulb A goes out, what happens to B, C, and D? Now remember, in order for the bulb to be illuminated, what happens, it has to have a complete path through the light bulb to the other end of the battery. So we start right here, and this right here has a complete path because I can go this way. Bulb B has a complete path because I can go this way. If you look in this case, it's the same path for both D and B. You can also, if you were on D, go this way. But the last one you want to look at is C, and C can go this way, and it can go through the C path as well. So both D, B, and C have complete paths, therefore they will light up. This question says your hairdryer suddenly stops working on one morning and your alarm clock shuts off, but the light remains on. How is this possible? If you were to look at it, you have a voltage source from the wall. What happens is if your hairdryer suddenly stops working, what you've done is you've had a break in the circuit. The alarm clock must be on the same circuit as the hairdryer, because when you break this circuit, this no longer functions as well. But the lights must be on a different path. And if the lights are on a different path and they can get back to the other end, this right here would function. We have what's called a series circuit. A series circuit is one in which the charges must flow through all of the connection. There's no alternative pathways. If I start right here, there's only one way for me to get through both this resistor and this resistor, and it's down this path. There's only one way for me to get through this resistor, and that's through this one path. So those are said to be series circuits. Now series circuits can be useful, but let's talk about a little bit more about what they are. A series circuit is like a one-lane road. All the cars can move in the same direction, but they have to move the same speed. If the car behind tries to go faster than the car in front, it doesn't work, they'll run into each other. So because of that, you can say that all of the charge is moving down the same path at the same time. If all of a sudden you have a break in the road and one car has to come to a stop, all of the charge has to come to a stop. A series circuit is really useful because if one connection goes out, they all do. You may be thinking that that's not particularly useful, but it's really useful when we talk about things like a circuit breaker or a fuse. If you have something that's potentially dangerous and there's too much current going through the circuit, you want to shut off all of the electrical devices as much as possible. So if the fuse were to melt and it wouldn't shut off the electricity here, that could cause a pretty big problem. There are also situations in which you need to experimentally manipulate the voltage. Things like a dimmer switch kind of work like this. So because of that, series circuits are really useful when you want to change the voltage that gets to a certain resistor or device, or if you want to shut off a circuit entirely. When you wire something in parallel, there's multiple ways for it to travel from one end to the other. So for example, you have the positive end of the battery. It goes through to this light bulb right here. This is another symbol for light bulb. And then you have multiple pathways at which it can go. It can go this way, or this way. Now remember, in order for the light bulb to light up, it needs a complete path. So if you were to break the circuit here, there's still a complete path here, just like we talked about before, needing a complete path. If you were to break it here, there would still be a complete path. So in this case, when you wire things in parallel, they still work even if you break the circuit in one location. Now, if you were to break it here, that'd be something totally different because there would be no path for it to go through. Now, we say that the charge chooses which path to go through. It doesn't choose, it doesn't sit there and think about it at a crossroads, but what happens is it always takes the path of least resistance. So say, for example, we still haven't really talked about this, but say this is a positive charge moving through the wire. And all of a sudden, this thing is broken, and you have a buildup of positive charges. Well, opposites attract and likes repel, so it's going to push away from that to another path. This positive charge wants to get to the negative end of the battery, so it's going to do it in the easiest possible way based on Coulomb's law. So a parallel connection is one that's very similar to a highway. Okay, you're looking at it in terms of multiple lanes. Okay, if you have one lane shut down, you can have one car go around it and go to the next lane. You can have it go around it and go to the next lane. You can have it go around and go to the next lane. There are multiple ways for it to go through. The cars move at different speeds. You have cars that are moving very slow here, and you have cars that are moving very fast over here. And so because of that, that's going to have some implications that we're going to talk about a little bit later. Parallel connections are useful whenever you want one resistor to go off, but you want the others to stay on, like a light switch. You don't want to turn on the light switch at your house and have the television come on, the light come on, the stereo come on, the fan come on, everything come on all at once that's plugged in. You'd rather control those things individually. And so because of that, you want parallel connections in your house as well. Each one of these outlets is wired in parallel. Okay? Each one of these things is wired in parallel. Switches and outlets are wired in parallel. And it's very useful for when you want voltage to stay the same. How are the resistors here connected? Well, remember, you have a light bulb, and a resistor right here. These are all examples of resistors. If you look, when I come through the circuit, I have to go through this one and this one. There's no way to go through either or. So you can say that these two are wired in series. If I go through this one, I have to go through this one. There's no alternative, so these are in series. So all of the resistors here are wired in series. If you look at this one, it says identify any two resistors that are wired in series. Well, if I have some sort of charge go through this one right here, then I can put it in series with any other resistor. I can say that these two are in series because if I go through this one, I gotta go through this one. I could say that these two are wired in series because if I go through this one, I got to go through this one. And I could say that these two are in series. So I can say this first resistor is wired in series with any of the other three. Identify any resistors that are wired in parallel. Parallel is where you have a choice, where you can go through this resistor or this resistor, or this resistor. And these three, when I get to this point right here, I can go this way, or this way, and still make it to the other end of the circuit. So these three resistors right here are said to be wired in parallel. This example says to draw a circuit schematic for 3 resistors wired in series connected to a voltage source. So you have a voltage source, you have 3 resistors, 1, 2, 3, that are all wired in series. Now a lot of people look at these two and say, isn't that parallel, these two right here? Because look, they're parallel to each other. But no, the answer is no. Remember, you have to follow the path. So if you follow the path right here, I start at the positive end. I have to go through this resistor in order to get to this resistor. So those are in series. I have to go through this resistor to get to this resistor. So those are in series. Okay, so now we talk a little bit more about fuses and circuit breakers. The advantage of a circuit breaker is that they're reusable. A circuit breaker is, you see a panel in your garage with these little switches that you can move back and forth. Those are examples of circuit breakers, and the reason why they're reusable is that when they get overheated, they just bend and they kick out the circuit. Okay, but the problem with a circuit breaker is it's generally expensive to install. You put them in your house, maybe in your car, and that's really about it. Fuses are everywhere. Remote controls, computer, all kinds of places. So because of that, fuses are really inexpensive, but they have to be replaced. They are not reusable. What happens is the current gets too much, it burns out, and whenever it burns out, it is no longer functional. You have to remove the fuse, put a new fuse in order for the circuit to work. Fuses are common in older construction homes. They tend to be updated with circuit breakers whenever there's major renovations, but you still do see houses with fuse boxes instead of circuit breakers. Since a properly wired fuse melts, what happens to the rest of the devices? And so we've talked about this. You have this idea of this voltage source, and there's a fuse right there, and then everything else that's behind it. So we put lots and lots of resistors behind it. But once you break the circuit, there is no longer a complete path for the charge to travel. So because of that, they all turn off. And the last example says a fuse wired in parallel will always melt. And this is kind of foreshadowing, I guess, a little bit at this point. But if you have this situation right here, where you have a fuse that is wired in parallel with a resistor, and they're connected to the other end of the battery. Okay, now what is the path of least resistance? Remember that a fuse has a resistance of 0, and this is a resistor. So because of that, all of the charge is going to travel through here. The more charge that travels through the fuse, the hotter it's going to get. The hotter that it gets, it melts. Okay, and that's just kind of a little bit of foreshadowing on the fact that you have this relationship between voltage and current and resistance that we will examine later.